An autonomous car is a vehicle that is capable of sensing its environment and navigating without human input. Autonomous vehicles feel their surroundings with such techniques as radar, lidar, GPS, odometry, and computer vision. Advanced control systems interpret sensory information to identify appropriate navigation paths, as well as obstacles and relevant signage. By definition, autonomous vehicles are capable of updating their maps based on sensory input, allowing the vehicles to keep track of their position even when conditions change or when they enter uncharted environments. Autonomous cars have control systems that are capable of analyzing sensory data to distinguish between different cars on the road, which is very useful in planning a path to the desired destination. Some demonstrative systems, precursory to autonomous cars, date back to the 1920s and 30s. The first self-sufficient cars appeared in the 1980s, with Carnegie Mellon University's NavLab and ALV projects in 1984 and Mercedes-Benz and Bundeswehr University Munich's Eureka Prometheus project in 1987. Since then, numerous major companies and research organizations have developed working prototype autonomous vehicles. Autonomous versus automated. Autonomous means having the power for self-government. Many historical projects related to vehicle autonomy have in fact only been automated due to a heavy reliance on artificial hints in their environment, such as magnetic strips. Autonomous control implies good performance under significant uncertainties in the environment for extended periods of time and the ability to compensate for system failures without external intervention. As can be seen from many projects mentioned, it is often suggested to extend the capabilities of an autonomous car by implementing communication networks both in the immediate vicinity and far away. By bringing in these outside influences in the decision process, some would no longer regard the car's behavior or capabilities as autonomous. For example, Wood al. writes, "This article generally uses the term autonomous instead of the term automated. We have chosen to use the term autonomous because it is the term that is currently in more widespread use. However, the latter term is arguably more accurate. Automated connotes control or operation by a machine, while autonomous connotes acting alone or independently. Most of the vehicle concepts have a person in the driver's seat, utilize a communication connection to the cloud or other vehicles, and do not independently select either destinations or routes for reaching them. Thus, the term automated would more accurately describe these vehicle concepts." Classification. In the United States, the National Highway Traffic Safety Administration has proposed a formal classification system. Level 0. The driver completely controls the vehicle at all times. Level 1. Individual vehicle controls are automated, such as electronic stability control or automatic braking. Level 2. At least two controls can be automated in unison, such as adaptive cruise control in combination with lane keeping. Level 3. The driver can fully cede control of all safety-critical functions in certain conditions. The car senses when conditions require the driver to retake control and provides a sufficiently comfortable transition time for the driver to do so. Level 4. The vehicle performs all safety-critical functions for the entire trip, with the driver not expected to control the vehicle at any time, as this vehicle would control all functions from start to stop, including all parking functions. It could include unoccupied cars. An alternative classification system based on 5 different levels has been published by SAE, an automotive standardization body. History. Experiments have been conducted on automating cars since at least the 1920s. Promising trials took place in the 1950s and work has proceeded since then. The first self-sufficient and truly autonomous cars appeared in the 1980s. with Carnegie Mellon University's NavLab and ALV projects in 1984 and Mercedes-Benz and Bundeswehr University Munich's Eureka Prometheus project in 1987. Since then, numerous major companies and research organizations have developed working prototype autonomous vehicles, including Mercedes-Benz, General Motors, Continental Automotive Systems, IAV, Autoliv Inc., Bosch, Nissan, Renault, Toyota, Audi, Volvo, Tesla Motors, Peugeot, Arca Technologies, Vislab from University of Parma, Oxford University and Google. In July 2013, Vislab demonstrated Brive, a vehicle that moved autonomously on a mixed traffic route open to public traffic. In 2015, those 4 states, together with Washington, D.C., will be joined by Virginia in allowing the testing of fully autonomous cars on public roads. As of July 2015, The Economist notes that automobile manufacturers draw a distinction between autonomous cars and self-driving cars. Car makers are keen to draw a distinction between autonomous cars and self-driving cars, and with good reasons of self-interest. Autonomous cars will look like the vehicles we drive today, taking over from the driver under certain circumstances. Self-driving cars are a stage further on. The steering wheel will disappear completely and the vehicle will do all the driving using the same system of sensors, radar and GPS mapping that autonomous vehicles employ. While some personal cars will remain, a fleet of shared vehicles will likely fill the streets of towns and cities. Transport systems. In Europe, cities in Belgium, France, Italy and the UK are planning to operate transport systems for driverless cars, and Germany, the Netherlands, and Spain have allowed testing robotic cars in traffic. In 2015, the UK government launched public trials of the Lutz Pathfinder driverless pod in Milton Keynes. Since summer 2015, the French government allowed PSA Peugeot Citroën to make trials in real conditions in the Paris area. The experimentations will be extended to other French cities by 2016 like Bordeaux and Strasbourg. The alliance between the French companies Thales and Valeo is also testing its own driverless car system. Potential advantages. An increase in the use of autonomous cars would make possible such benefits is avoid traffic collisions caused by human driver error such as reaction time, tailgating, rubbernecking and other forms of distracted or aggressive driving, increased roadway capacity and reduced traffic congestion due to reduced need for safety gaps and the ability to better manage traffic flow, relief of vehicle occupants from driving and navigation chores, higher speed limit for autonomous cars, removal of constraints on occupants' state. In an autonomous car, it would not matter if the occupants were underage, overage, unlicensed, blind, distracted, intoxicated, or otherwise impaired. Reduction of physical space required for vehicle parking, and vehicles will be able to drive where space is not scarce. Reduction in the need for traffic police and premium on vehicle insurance. Reduction of physical road signage. Autonomous cars could receive necessary communication electronically. Smoother ride. Reduction in car theft due to the vehicle's increased awareness. Increased ergonomic flexibility in the cabin, due to the removal of the steering wheel and remaining driver interface, as well as no occupant needing to sit in a forward-facing position. Increased ease of use of large vehicles such as motorhomes, when used for car sharing, reduces total number of cars. Enables new business models such as mobility as a service which aim to be cheaper than car ownership by removing the cost of the driver. Elimination of redundant passengers. The robotic car could drive unoccupied to wherever it is required, such as to pick up passengers or to go in for maintenance. Potential obstacles. In spite of the various benefits to increased vehicle automation, some foreseeable challenges persist. Liability for damage. Liability may continue to lie with both the automaker, as well as the individual owner. Resistance by individuals to forfeit control of their cars. Software reliability. A car's computer could potentially be compromised, as could a communication system between cars by disrupting camera sensors, GPS jammers, spoofing, implementation of legal framework and establishment of government regulations for self-driving cars. Drivers being inexperienced if situations arose requiring manual driving, loss of driving-related jobs, resistance from professional drivers and unions who perceive job losses, loss of privacy, sharing of information through V2V and V2I protocols, competition for the radio spectrum desired for the car's communication. Self-driving cars could potentially be loaded with explosives and used as bombs. Ethical problems analogous to the trolley problem arise in situations where an autonomous car's software is forced during an unavoidable crash to choose between multiple harmful courses of action. Susceptibility of the car's navigation system to different types of weather. Autonomous cars may require very high-quality specialized maps to operate properly. Where these maps may be out of date, they would need to be able to fall back to reasonable behaviors. Current police and other pedestrian gestures and non-verbal cues are not adapted to autonomous driving. Current road infrastructure may need changes for autonomous cars to function optimally. Some examples include traffic and street light upgrades that communicate with autonomous vehicles. Policy implications. If fully autonomous cars become commercially available, they have the potential to be a disruptive innovation with major implications for society. The likelihood of widespread adoption is still unclear, but if they are used on a wide scale, policymakers face a number of unresolved questions about their effects. One fundamental question is about their effect on travel behavior. Some people believe that they will increase car ownership and car use because it will become easier to use them and they will ultimately be more useful. This may in turn encourage urban sprawl and ultimately total private vehicle use. Others argue that it will be easier to share cars and that this will thus discourage outright ownership and decrease total usage, and make cars more efficient forms of transportation in relation to the present situation. Legislation in the United States, state vehicle codes generally do not envisage, but do not necessarily prohibit, highly automated vehicles. To clarify the legal status of and otherwise regulate such vehicles, several states have enacted or are considering specific laws. As of the end of 2013, 4 U.S. states, along with the District of Columbia, have successfully enacted laws addressing autonomous vehicles. In June 2011, the Nevada legislature passed a law to authorize the use of autonomous cars. Nevada thus became the first jurisdiction in the world where autonomous vehicles might be legally operated on public roads. According to the law, the Nevada Department of Motor Vehicles is responsible for setting safety and performance standards, and the agency is responsible for designating areas where autonomous cars may be tested. This legislation was supported by Google in an effort to legally conduct further testing of its Google driverless car. The Nevada law defines an autonomous vehicle to be a motor vehicle that uses artificial intelligence, sensors and global positioning system coordinates to drive itself without the active intervention of a human operator. The law also acknowledges that the operator will not need to pay attention while the car is operating itself. Google had further lobbied for an exemption from a ban on distracted driving to permit occupants to send text messages while sitting behind the wheel, but this did not become law. Furthermore, Nevada's regulations require a person behind the wheel and one in the passenger's seat during tests. In 2013, the government of the United Kingdom permitted the testing of autonomous cars on public roads. Prior to this, all testing of robotic vehicles in the UK had been conducted on private property. In 2014, the government of France announced that testing of autonomous cars on public roads would be allowed in 2015. 2,000 kilometers of road would be opened through the national territory, especially in Bordeaux, in Isère, Île-de-France and Strasbourg. At the 2015 ITS World Congress, a conference dedicated to intelligent transport systems, the very first demonstration of autonomous vehicles on open road in France is proposed to be carried out in Bordeaux in early October 2015. In spring of 2015, the Federal Department of Environment, Transport, Energy and Communications in Switzerland, short UVEK, allowed Swisscom to test a driverless Volkswagen Passat on the streets of Zurich. Vehicular communication systems. Individual vehicles may benefit from information obtained from other vehicles in the vicinity, especially information relating to traffic congestion and safety hazards. Vehicular communication systems use vehicles and roadside units as the communicating nodes in a peer-to-peer network, providing each other with information. As a cooperative approach, vehicular communication systems can allow all cooperating vehicles to be more effective. According to a 2010 study by the National Highway Traffic Safety Administration, vehicular communication systems could help avoid up to 79% of all traffic accidents. In 2012, computer scientists at the University of Texas in Austin began developing smart intersections designed for autonomous cars. The intersections will have no traffic lights and no stop signs, instead using computer programs that will communicate directly with each car on the road. Among connected cars, an unconnected one is the weakest link and will be increasingly banned from busy high-speed roads, predicted a Helsinki think tank in January 2016. Public opinion surveys. In a 2011 online survey of 2006 US and UK consumers by Accenture, 49% said they would be comfortable using a driverless car. A 2012 survey of 17,400 vehicle owners by J.D. Power and Associates found 37% initially said they would be interested in purchasing a fully autonomous car. However, that figure dropped to 20% if told the technology would cost $3,000 more. In a 2012 survey of about 1,000 German drivers by automotive researcher polls, 22% of the respondents had a positive attitude towards these cars. 10% were undecided, 44% were skeptical and 24% were hostile. A 2013 survey of 1,500 consumers across 10 countries by Cisco Systems found 57% stated they would be likely to ride in a car controlled entirely by technology that does not require a human driver, with Brazil, India, and China the most willing to trust autonomous technology. In a 2014 U.S. telephone survey by Insurance.com, over three-quarters of licensed drivers said they would at least consider buying a self-driving car, rising to 86% if car insurance were cheaper. 31.7% said they would not continue to drive once an autonomous car was available instead. In a February 2015 survey of top auto journalists, 46% predict that either Tesla or Daimler will be the first to the market with a fully autonomous vehicle, while Daimler is predicted to be the most functional, safe, and in-demand autonomous vehicle. In 2015, a questionnaire survey by Delft University of Technology explored the opinion of 5,000 people from 109 countries on automated driving. Results showed that respondents, on average, found manual driving the most enjoyable mode of driving. 22% of the respondents did not want to spend any money for a fully automated driving system, whereas 5% indicated they would be willing to pay more than $30,000, and 33% indicated that fully automated driving would be highly enjoyable. 69% of respondents estimated that fully automated driving will reach a 50% market share between now and 2050. Respondents were found to be most concerned about software hacking, misuse, and were also concerned about legal issues and safety. Finally, respondents from more developed countries were less comfortable with their vehicle transmitting data.